name is Bart Geerts. I'm from the Department of Atmospheric Sciences at the University of Wyoming, and I'm here to talk about a recent field campaign deploying the ARM mobile facility to northern Scandinavia, the COMBLE experiment, COMBLE, cold air outbreaks in the marine boundary layer experiment, conducted between the 1st of December of 2019 through the 31st of May of 2020, during the height of the pandemic, actually. The experiment did conduct effectively its entire operation, even though the pandemic was raging there for a few months, starting in mid-March, I guess, of 2020, as you recall. Anyway, one of the largest air mass transformations occurs on Earth when cold air masses, say Arctic air masses, flow off the Arctic ice sheet and over the warm, relatively warm waters, open waters of the far northern Atlantic. There's a few other places on Earth where this happens, and the cold air outbreak cloud regime, as we call it, is actually rather ubiquitous. You can see it off, say, in North America, the East Coast, when cold continental air masses in winter blow off the North Atlantic, Mid-Atlantic coast, and even further south. This cloud regime appears beautifully on satellite imagery, well recognized as a series of cloud streets initially evolving to a more open cellular structure. So that's what the COMBLE campaign is about, and the transformation of the air masses involves intense surface heat fluxes, developing convective boundary layer that rapidly assumes clouds and precipitation, whose properties are mediated by aerosol concentration and properties. And the cloud structure then evolves from linear to cellular, typically, in a fashion that is not readily understood and certainly not readily simulated in say, large eddy simulations. And larger scale models, cloud resolving numerical weather prediction models or climate models, have a hard time representing this cloud regime, because the cloud regime actually falls in a dynamic gray zone where these convective processes, boundary layer processes, and cloud and precipitation processes are fully coupled and cannot be separately parameterized. So the COMBLE campaign then examined these clouds as they've drifted off from the Arctic ice edge some 1,500 kilometers further north, down across the Norwegian Sea and towards our main site at 69 degrees north, at the site near Andenes, which was equipped with a series of in situ and remote sensing instruments to document the meteorological conditions, surface fluxes, the vertical structure as well as a horizontal structure of the precipitation systems, cloud properties, aerosol properties, a very rich array of scanning and vertically profiling remote sensors and in situ sensors to document this cloud regime. There was an additional site called Bear Island, or Bjørnøya in Norwegian, a remote island at 75 degrees north, where a set of ARM instruments was deployed as well for the duration of the campaign. The full array of instruments at these two sites provides an excellent data set to fundamentally understand the cloud processes, and mixed-phase cloud processes in particular, and its representation in large eddy simulations as well as climate models. And this environment is particularly suitable in the context not only of the Arctic amplification, the amplified response to global change that we see in the Arctic, but also because this cloud regime has a well-defined origin, a well-defined upstream starting point, if you like. And in addition, COMBLE documented a fairly broad range of temperature, wind, and aerosol conditions to evaluate, validate, and ultimately improve the representation of cloud processes, mixed-phase cloud processes in these models.